Katrina.
And I'm Kelly. And in this lab we worked with an operational amplifier, or op-amp. An op-amp behaves like a voltage-controlled voltage source. Op-amps are designed to perform mathematical operations. We used the function generator as a power supply, and that is connected to the inverting input of the op-amp. This means that our gain should be negative R2 over R1.
And we used LT-Spice to build a simulation of what this circuit should look like when we build it in the lab. So let's take a look at that. Here is our LT-Spice simulation. The power supply is a sine function from our function generator. We have two resistors, R1 and R2. R1 is connected to the inverting input, and R2 is connected to the output op-amp. We have a positive 15 volts and negative 15 volts connected to the op-amp. We originally intended for R1 to have a value of 100 ohms and R2 to have a value of 1K.
Later in the lab, we ran our circuit and realized that our gain had a value that wasn't what we were expecting. If R1 was 100 ohms and R2 was 1K, then our gain should have been about 10, but we were getting a value of around 8. So we measured each resistor using the DMM and found that R2 had a value of about 820 ohms. So we had to adjust our LT-Spice simulation to reflect this.
Here is the actual circuit that we built in lab. It has a function generator, power supply, breadboard, and DAC, which is connected to our computer, where we have made a LabVIEW VI to measure the gain of our circuit.
The power supply provides the positive 15 volts and negative 15 volts that are connected to our op-amp. The function generator provides the sine wave that we are testing to see if the op-amp will amplify. It is going through the first resistor and into the inverting input of our op-amp. So the output sine wave should be out of phase with the input wave function.
Here's our breadboard with the op-amp, which is an LM348. We referred to the datasheet to determine how to set it up in the circuit. Pin 4 is where we connected the positive 15 volt power supply, and pin 11 is where we connected the negative 15 volt power supply. These are labeled VCC plus and VCC minus in the diagram. We used pins 5 through 7 for our inputs and outputs of the op-amp. Pins 5 and 6 are the inputs.
Pin 5 is connected to ground and is our non-inverting input. Our inverting input, pin 6, is connected to our R1 resistor, which has a resistance of 100 ohms. Pin 7 is the output of the op-amp, and we connected it to our 820 ohm resistor.
We connected our DAC to our circuit to read in the voltage both at the input and the output of our op-amp. Positive AI0 is connected to pin 6, and positive AI1 is connected to pin 7 in our circuit. Recall that pin 6 is the input of the op-amp and pin 7 is its output. Negative AI0 and AI1 are connected to ground.
So this is our VI. On our block diagram, we have a DAC. It reads in two channels, AIO and AI1. It reads in 1,000 samples at 20,000 samples per second. We tried a rate of 80,000 samples per second, but that was too fast. We made a graph of the data, which can be seen on the front panel. 8 volts is the output, and 1 volt is the input to the op-amp. The tone measurements measure the amplitude and phase of the sine function output by our function generator. The voltage output divided by the voltage input gives us our gain. The difference between the two phases should be 180 degrees because inverting op-amp means signals out of phase. We added 360 degrees if the readings were negative. We have our gain and phase indicators on our front panel with a gain of about 8 and a phase of about 180. This agrees with our LT-Spice simulation.